Good morning, good day, and good evening to everyone. Thanks for joining us. Let me start with a few rules we propose during the seminar. So first of all, try your best to keep your microphones and videos off. You will be able to switch on your microphones. Today, we have three ways to ask questions. You may want to raise your hand and we will interrupt the speaker. You may also type your question to the chat, or the speaker kindly allowed to interrupt him and ask your questions, but please do not go to discussion during the seminar. So discussion may be during the question part in the very end, I mean the very long one. So our today's speaker, I'm very happy to introduce Professor Yonatan Sivan from Ben-Gurion University, Israel. So the title of the talk is Hot Electrons in Nanoplasmonic Systems, Reality of Fake News. Yonatan, please.
Okay, I'd like to start by thanking you, Anton and Georgi, and obviously Pavel, for giving me the opportunity to speak here today. I will present work which is done with in collaboration with a series of colleagues. I mentioned all of them. I think this is a very unique talk, so I would appreciate questions on the way. Especially, it's important. It's a good talk for students. So I hope you will enjoy this talk. I'll now stop the video for my. For myself and focus on the slide. So just to start, let's see, yeah, no, yes. So just to introduce myself, so I'm coming from Israel, which is this tiny place on the corner of the Middle East, which is always on the news, and more particularly, if I use the children's map from my children, I'm working in Beersheba. It's the city which is at the southern part of Israel. It's the fourth largest city in Israel and the youngest campus university in Israel. And in this institute, I'm leading a group where we do analytical and computational work in linear and mostly non-linear nanophotonics. So before we get to the actual topic for today, let me say a few words about the work done in my group. So in the past, we have had a lot of interest in short pulse dynamics with all sorts of exotic systems, like where the optical properties change in time. We are looking at slow and stopped light, all sorts of bizarre wave mixing. We have a large effort in the context of computational electromagnetism, where we're developing new, very efficient, very fast computational technique based on mode calculations, which allows us already to demonstrate speeds orders of magnitude faster than what you could do in commercial software. I'll obviously be happy to discuss any of these topics later on. But I think the majority of the activity of my work, it's going to be correct to say that it's in the context of nanoplasmonics. We were interested in the past in using metal nanoparticles to assist super resolution microscopy techniques. We're looking at wave mixing, nonlinear optics, using metal nanostructures, where we employ the famous transformation optics technique, which became famous for invisibility cloak design, etc. We apply it also to nonlinear media. And a very large part of the efforts in my group is dedicated to understanding the thermal response of metal, thermal nonlinear response, be it in the very fast timescales where we look at diffusion and all sorts of phenomena that have not been considered before, somewhat surprisingly, and also at the context of at the opposite limit, where we're looking at the ultra slow response, the steady state response to continuous wave illumination. So indeed, the common denominator for these studies is nanoplasmonics. in principle, interaction of light with small nanoscale metallic nanostructures, and I'm sure that many people in the audience are aware of great interest, growing interest in these systems. So there's a very long list of cool applications and increasing, exponentially rising number of publications over the last 2 decades. These applications are mostly based on the fact that metals exhibit a negative real part of their permittivity, which allows to guide light along them, focus light strongly around them, etc. So that's the underlying physical principle behind these applications. However, anyone who has even a little experience in plasmonics knows that metals also are strongly absorbing the light, and because of that, most people will argue that the really successful or the more applications with more potential for success are those which are either insensitive to absorption or those which actually rely on absorption. And these include, for example, high temperature chemistry and thermal treatment of cancer, sanitation. And for today's talk, I'll focus on one of the maybe more exciting recent suggested applications of nanoplasmonics, which rely on absorption, which is photocatalysis. So photocatalysis brings us to the domain of chemistry, nanochemistry, although I think many of you that have looked at know my background or have seen the type of projects that we're leading can appreciate that I'm no chemist. So what I want to start with is to introduce a very naive, very simplistic picture of what catalysis is. You can consider this as the physicist view of catalysis, and I will focus on only the essential aspects of the problem which will be relevant for the results that I want you and ideas that I want to introduce in today's talk. So, literally speaking, catalysis is about speeding up chemical reactions. Obviously, you can appreciate that this is a very large part of the efforts of humanity in the context of generating green fuels and phosphorus and materials for agriculture. So the idea in catalysis is to, if we think about a typical chemical reactions, the customary approach in chemistry, schematic, is to plot the various states on an energy scale along some reaction coordinate. This can be space for a simple molecule, or maybe something more sophisticated for complicated molecules. Anyhow, you should follow now the blue line, and I hope that you're seeing my cursor. So basically, it describes the landscape, the energy landscapes that the reactants are filling. So initially, they are in the initial state. And in order to reach for the reaction to happen, they have to reach the product state. For that, they have to gain some quantum of energy, which we denote by epsilon 0. Okay, this can happen, for instance, by colliding with molecules in the environment or something like that. And the probability of this to happen is given by the exponent of the ratio of this characteristic energy scale called the activation energy and the temperature. Okay, this is a fairly fundamental rule that we know already for more than 100 years from the time of Arrhenius, okay, the late 19th century. So basically the idea is to, in catalysis, is to mix the reactants with nanoparticles. And in this case, the presence of the nanoparticles causes the reactants and the system to modify in the sense that a new pathway is being activated. You can think about this as the orange line, this that's shown here. And a typical thing that can happen, the molecule may be charged because the electron tunnels to the reactant. And then the point is that the energy barrier or catalysis will be effective when the energy barrier of this new pathway, epsilon 1, will be smaller than the original pathway. So this means that the reaction can be exponentially more sensitive, more faster compared to what we had before when we didn't have the particle, when we had just the blue pathway. Okay, obviously, since these reactions are activated by these electrons that have to tunnel and react, have to react with the molecules, the rate of the new pathway is also proportional to the number of high energy electrons that are available in this specific system. Okay, so how many of those we have? If we think about a typical metallic catalyst, the electron distribution follow a Fermi-Dirac statistics, which is shown here schematically. It means that the number of electrons with high energies is exponentially small. We are familiar with this typical exponential decay. So the higher the energy that is needed for the reaction, the fewer electrons that we have. Okay, so this makes typically the reaction not go so fast. But this understanding also reveals to us the way to improve the rate of the reaction. This can be done simply by heating. Indeed, the range where or the rate at which the distribution decays is inversely proportional to the temperature of the electrons. So that if we increase the temperature, this distribution smears out, it becomes broader, and we have exponentially more electrons in the high energy, and the reaction is exponentially faster. However, at the same time, also the expenses, if you think about this in the commercial industrial level, if you have to raise the temperature of huge volumes of reactants, where you want to catalyze the reaction, heating large volumes is not a cheap process. So this is industrial, on the industrial level, this is problematic. Further on, the heating also may catalyze also additional chemical reactions that we are not interested in. So this will also reduce the yield or the efficiency of the process that we are looking at. Okay, this means that the thermal pathway to increase the reaction rate is not selected. So this means that overall the chemists consider heating as not such a good idea, not such a good solution for making reactions fast. In this context, in the last decade, or more than a decade ago, people starting thinking of an alternative solution. The idea is the following. We would like to use plasmonic nanoparticles because they have two key properties that we need. First of all, they have many electrons. That's what is typical for metals. They have lots of free electrons. Secondly, they absorb light very efficiently. Okay. Now, I should point out at this stage already that if you are thinking about applications, you really ought to think about what happens in the steady state, okay? To think what happens under continuous wave illumination, because again, if you think about this in the industrial level, you want to illuminate large volumes, you want to work with large volumes of materials. This cannot be done with fancy ultra-fast lasers. Okay, so once we illuminate the metal particles in our metal catalyst in our system, we generate essentially many more electrons with high energy. So essentially we take, if you think about, you look at this distribution, the blue line is what we have initially, and the initial distribution would take electrons from this region or also from this region and move them up to energies which are at a higher, much higher than the Fermi level. Okay, so these are the electrons that we need for the reaction. So somewhat confusingly, these non-thermal carriers, these excited electrons are called hot electrons, but this actually means that they are non-thermal in the sense that the distribution, if you look at the dashed red line, is characterized by it cannot be characterized by a Fermi-Dirac distribution. You can see these shoulders that do not follow the Fermi-Dirac distribution. Okay, so this is a confusing name. This is the jargon, so I'm not going to, I don't have much to say about this. I'll just stick using the concept either hot electrons, by which I mean non-thermal electrons. All right. So to give you an idea, an impression of how exciting these ideas, I show here a non-exhaustive collection of papers published in glossy journals, high-impact journals, which all reported faster chemistry in the presence of illuminated metal nanoparticles. This is coming from many different groups. If you think about this in terms of funding in the US only, over the last decade or so, the funding that was spent on these research directions is on the level of $100 million US. So this is a massive effort of the scientific community, if you wish. Now, if I have to summarize the findings, then I would say that in just one sentence, then I would say that the experiments have been reporting faster reactions by about 10 to 100 times. Okay, and these are fantastic news. If you think about our ability to generate green fuels, 100 times faster is excellent news for humanity. However, we all know that, I mentioned this, is that once the electron is excited from, say, this point and goes up to a higher point in the distribution, then it quickly also collides with other electrons, with other phonons. We'll see this explicitly later in our theoretical model, and this causes them to lose energy. In this process, the distribution smears out. You can see that it broadens, okay, because there's more energy, more electrons with high energy above the Fermi energy, which is here in the middle, okay? So, and this smearing out is basically amounts for heating up the system. This process is called thermalization, okay? So one can wonder whether the illumination also causes heating, or another way, whether heating can also explain or contribute to the faster chemical reactions. So it seems that in order to answer the practical question about the origin or the reasons for the faster chemistry, we have to understand, to answer a very basic physical question, which essentially is, to understand, we need to understand upon absorption of a photon, how does the energy of this photon split between the generation of heat and pushing the system away from thermal equilibrium, between the generation of non-thermal carriers. Now, there's been decades, I indicate here a few, very, very few notable groups. Obviously, this list does not do justice to all the groups that have ever worked on this topic. There's a lot of research done on pulsed illumination. A short pulse comes in, then it's pretty clear what is happening. The non-thermal the electron distribution is initially non-thermal, then there is this thermalization process, and eventually the system heats up. This is perfectly well understood. However, what happens when you continuously illuminate the system is a much less understood question. In fact, it was hardly studied until the last few years. If you do look at the literature from the last decade or so, and you want to understand what's the answer for this question, how does the energy split between heating and non-thermal distribution, the impression you will get is that there's a very strong non-thermal carrier generation and there's essentially no heating. This sort of result or implicit result is in a sense motivated by a hidden assumption. So most physicists would argue that once you have a metallic system which is out of equilibrium, you cannot define you cannot fit it with a Fermi-Dirac distribution, at least not uniquely. So there's no point about talking about temperature at all. However, we know from our day-to-day experience that if we shine light on metals, if we put a piece of metal in the sun, it does heat up. You don't need to be a scientist in order to know that. So there seems to be some conflict, some paradox between these two views, if you wish. And in fact, to strengthen this argument, not only we know this from our daily experience, we also know this from a very efficient, a very pronounced line of research, which is called thermoplasmonics. This is led by people like Guillaume Baffou and Roman Kidan, Sasha Kovov, many others again, which have been promoting over the last at least 15 years applications which are based on using metal nanoparticles as heat sources. And in fact, when people are modeling or describing the results in this context of thermoplasmonics, then most studies are based on just modeling with a single temperature. Some use more sophisticated modeling, which involves two separate temperatures, one for the electrons and one for the phonons. So this makes this paradox potentially even more complicated. Okay, so it seems already that in order to understand this practical question, we also have to go deep into the fundamental physics and resolve some very basic disagreements between different views. Okay, so what the plan for my talk today is to show you two things. First, I'd like to show you to present a self-consistent theory which allows us to treat the non-thermal distribution, the non-equilibrium distribution in the electron system together with electron heating and lattice heating, the heating of the phonons. And in that sense, we will reconcile, if you wish, the paradox that I have just mentioned. Once we do that, we'll show that the claims about the dominance of hot electrons over thermal effects are simply not correct. Once we have this theory in hand, the second part will be to look into these sets of experiments that have reported faster chemical reactions in the presence of illuminated metal nanoparticles, and to identify, we'll do two things. We'll identify errors in some of the more famous experiments on the topic, and then we'll use our theory to provide an alternative quantitative thermal explanation for this, for these experiments. Just to give you an idea, here's a collection of papers we looked of results from papers we looked at from various groups, different reactions, different systems, different materials. In all of these papers, we took the data, and all the solid lines that you see are basically our theory fit to the results, and it's based purely on thermal theory. So all this will eventually be hopefully very clear. So I would like to start now. Before I start, I should obviously acknowledge the great work done by the people with whom I collaborated on this project. So the first of them is Dr. Ben-Gurion, very talented postdoc who is responsible for the sophisticated thermal calculations that you will see along in the second part, essentially. More so, I would like to thank Professor Yoni Dubi, an excellent scientist and a very close friend with whom I've been doing this research. Essentially, I could not have been doing any of what I'm showing today without the help of Yoni. This has been, in that sense, a successful and very enjoyable project. So let's start with the first part, with the theory. At this point, I would like to also encourage people listening to interrupt me with questions. If things are, if I'm going too quickly, if there's things that are not clear, indeed, do feel free to interrupt me or raise hands. I'm very much welcoming any questions during the presentation. We have plenty of time. Okay, so again, the first part is the theory of calculating how the electron distribution looks like in an illuminated metal system. And for that, we adopt what is probably the simplest possible model, which is basically the Boltzmann equation for F, which is the electron distribution function. Okay? In order to determine it, we account for the three most generic processes. First, photon absorption, then electron-electron scattering, and electron-phonon scattering. There's obviously other effects, but typically those are weaker, smaller. We added them later. You can ask me about that maybe later, but overall, these are the dominant effects that have to be accounted for. As you probably know or be able to appreciate, each of them has been very extremely well studied, typically with a Fermi golden rule type formulation, and all the description is very well accepted. All the parameters are known. I'm listing here again some of the groups that have studied or developed these modeling. So we are, in that sense, not doing anything new. Let me just introduce to you each of these terms separately. So let's start with photon absorption. So we specifically adopted a very elegant formulation developed by Tamar Zagman and Avraham Nitzan, where basically the change of population due to photon absorption is given by the product of NA, that's the density of absorbed photons. That's essentially the input from electromagnetic calculations through the Poynting theorem. Okay, it's proportional to the square of the electric field. Okay, and this multiplies the probability of a transition of an electron, which is itself proportional to the probability of finding an electron at state epsilon, and finding a hole at an energy which is h bar omega higher. Okay, that's a very standard way to describe this process. If I am now showing this graphically, so this looks like the red line here, okay? So essentially you can see that the Fermi energy is in the center, so above the Fermi energy I'm gaining electrons, there's a positive value, below that I'm losing electrons. This is just because energy is being shifted to higher energies, higher electron energies. Okay, so this sort of behavior is consistent, obviously, with the photoelectric effect. Okay, so although the Boltzmann equation may be considered as semi-classical, it's actually semi-quantum, we would argue, because it exhibits this essential quantum feature of the problem. Just to compare, I show you also here the black line. This is taken from a very detailed study of the group of Sasha Govorov, which performed the fully quantum calculations where in the electron states have been quantized. And as you can see, even for nanoparticles, which is as small as 2 nanometers, both gold and silver are the semi-quantum formulation reproduces the exact fully quantum calculation to a very good extent. Okay, so this allows us to conclude that quantum effects in this context are fairly small. Okay, so this is about photon absorption. Secondly, electron scattering. So what I write to you is a very, very long equation, which I definitely don't want to dwell onto. The idea is that electron-electron interactions is a very complicated process. It involves 2 particles going in, 2 particles going out, energy, momentum conservation, various things can happen, as you can appreciate from the complexity of this triple integral over energy, etc. So the only thing I want you to appreciate is that, first of all, computationally, this is a nightmare doing this calculation properly. Secondly, it's not so clear from this term, what is the system trying to do? What's the underlying physics? What is the system trying to reach? What state does it aspire to reach because of all these scatterings? Okay, and this will be key to the next to our own take on the solution of this problem. Lastly, I should mention here, there is electron phonon scattering again. It's given by a complicated integral that I really don't want to explain. Only thing I want you to appreciate is 2 things. Actually, first of all, this is based on well-established approach in solid-state physics. It's essentially assuming the phonon system is in sort of equilibrium. This is something you can relax. And basically, there's a balance here of various phonon emission and absorption processes. They are all plotted here in the inset. As you can see, that they're more or less the same. So the processes that generate electrons and take away, sorry, phonons or electrons, and take away electrons nearly balance each other. So if the individual rate of each of these terms can be as fast as 10 femtoseconds, the balance, the total balance between emission and absorption events of phonons is far slower. So typically on the level of 1 picoseconds for, say, if the electron system is a bit hotter. Then it has this characteristic shape, which, as you can appreciate, has a negative value above the Fermi energy and positive below. This basically means that the electron system is losing energy. Okay, if the electron system is hotter, it will transfer energy to the phonons, so it's losing electrons with high energy and gaining electrons with low energy. That's it. Okay, that's what we need in order to understand this system later. All right, so again, this is our equation. It's completely standard formulation. What we did, however, which is different from the others from previous works, is that we looked at it in the context of continuous wave illumination. Namely, we wanted not to see how this evolves in time, but actually to see the balance of these 3 terms in the steady state. Okay? Now, when we did this, we introduced 2 key elements. The first is that instead of the complicated electron-electron interaction, scattering integral that I showed you before, we adopt a so-called relaxation time approximation. What does this mean? It means that we simply introduce the basic physical fact that the electron system wishes at some point in the future to reach a thermal Fermi-Dirac distribution at some unknown electron temperature. Okay, and it is doing this and this is actually a fact that I think is not under any debate. It's doing this in some characteristic time scale, which is marked here by tau EE. There's various ways to write down the expression for this time scale, be it Fermi liquid theory or more sophisticated, more recent calculations from people that I already mentioned. You can see the typical way this timescale depends on energy. The point is that if electrons are very far away from the Fermi energy, this rate can be very, very fast. It can be few femtoseconds. Okay. Now, the advantage of this approach is threefold. First of all, it tells us exactly what the physics of the system is. It tells us what the system wants to do to reach some temperature, some thermal distribution. And it also allows us to separate the thermal part of the distribution from the non-thermal part of the distribution. And as you remember, this is essentially our goal. Okay. Secondly, and not less importantly, this makes the whole calculation much simpler to perform. And as we a posteriori verified in various ways, this is an excellent approximation to the actual triple integral scattering integral. All right. So that's the first key ingredient. The second one is that we determine the electron and phonon temperatures from nothing but energy conservation. This sounds trivial, but in fact, this was not done before. So specifically what we did is to ensure that the amount of energy going into the metal system due to photon absorption is perfectly balanced by the amount of energy leaking out to the environment as heat. So the crucial point to appreciate is that this rate of particle losing energy to the environment depends on the particle shape. Bigger particles lose a different amount compared to small particles. And also it depends on the thermal properties of the host. Okay? So for instance, a particle in air would lose less energy, less heat to the environment compared to a particle in a semiconductor. Now, as I emphasized, all these considerations were completely absent in all previous studies. This is probably because previous studies have been focused on ultra-fast case and only in the electron systems. And there's very good reasons why these considerations have been ignored so far, but this makes previous works not obey proper energy conservation in the whole electron, photon, phonon environment system.
Jonathan, excuse me.
Basically, yeah, this basically distinguishes our work from previous ones. Yes.
We have a question.
Yes.
From Mihail Petrov.
Yeah.
Yeah, thanks, Anton. Thank you, Anton, for the talk. But I got a question. So here you give this balance between the absorbed and energy transfer to the system. But can it be somehow? Is there any channel which can, like emission of secondary photons or things like this? Can be this energy re-emitted into light? Because that's not somehow counted as far as I see here. So does this kind of processes, maybe electron emission or photon emission, what part of energy does it bring? So what's the amount?
Excellent question. Thank you. Excellent question. So indeed, what we considered so far is just the three generic processes: electron scattering, electron phonon scattering, and the photon absorption. There's additional processes like electron emission, photoluminescence for metals. We all know that this is something that is happening, and it has been measured, but typically these effects are much, much weaker, much slower. To be specific, the efficiency of emission of light from metal particles has a quantum yield of 10 to the minus 10. maybe higher for particles, but it's typically smaller. What I'll show towards the end of the talk is how we use the model that I presented so far also to study exactly these effects. Okay?
Jonathan, any values? So, or you want announce them? You'll talk about them later, right?
So I think the quantum yield of these processes is the characteristic value. So if you think about quantum yield of 10 to the minus 6, it means that this process is typically, and obviously this depends on particle shape, etc., but typically it's about 1 million or so weaker than all the other processes that I've been discussing here. Okay? But anyhow, these processes can be accounted for in our formulation. It won't make a big difference, and we actually do this later on, as I hope to show you. Okay, so probably towards the end, you will get some insight about, some maybe more quantitative answer about for your question. All right, so back to this context of energy conservation, let's be a bit more specific. So how do we ensure this energy conservation? So what we do is integrate, we want to calculate the total energy held by the electron system. So essentially we integrate over all the electrons by multiplying them with the density of states and the energies, and we get an dynamic, and we convert this way the Boltzmann equation. So the Boltzmann equation from to an equation for the total energy of the electrons. So I write this here. I introduce this compact notations, different rates for energy transfer rate to from electrons to phonons, and due to photon absorption. If I write this just with this compact notation, you can see that, well, this looks simpler. Just to make it more schematic, I also use the fact that this complicated integral can actually be very well approximated with a simple expression, which involves a characteristic energy, electron-phonon coupling coefficient times the difference between the electron and phonon system. This is a very, very well-known approximation. So this is about the electron energy. The next step is to complement it with an equation, a phenomenological equation for the phonon energy. Okay, so specifically, whatever energy that the electron system loses to the phonons ends up heating up the phonons. Okay, so that's the complementary term. And we also allow, as I said, energy to leak to the environment using the same type of term. So there's some phenomenological coefficient that tells us the rates of energy leakage to the environment, and it's proportional to how much hotter the phonon system is compared to the environment. Obviously, you can make this model much more complicated. For the moment, we are focusing on the essence, so we look at the simplest possible model where this value is taken from experimental measurements. Okay, so those which are a bit more familiar to this topic may already appreciate that what we have here is essentially the so-called two-temperature model for the dynamics of heat in a metal. The only thing that we did here is we coupled it and derived it self-consistently from the Boltzmann equation for the specific electron distribution. So again, this should ensure you that what we are doing here is fairly standard and well established. All right. So far this was the theory. Let's look at some results already. So so I'll show you the generic, most simple plasmonic system, which is a 5 nanometer radius, small radius silver sphere, so that I can ignore interband transition. It's illuminated at its Plasmon resonance. So what I'm plotting here is the difference between the steady state distribution and the thermal distribution. I'm doing this for different illumination levels. You can see that they're quantitatively the same, qualitatively the same. And in order to capture the many length scales, orders of magnitude that we have in the system, I'm plotting this on a logarithmic scale, and this forces me to point out that regions, for instance, above the Fermi energy correspond to positive values. These are hot electrons. Below, these are called hot holes. Yeah. So what the obvious feature of this of the results that we have is that most of the change of the electron distribution occurs near the Fermi energy, and in fact, if I'm now plotting this on a linear scale, then I see that indeed it's positive above the Fermi energy and negative below, and this essentially has the same form as the difference between two thermal distributions, say at 301 degrees and 300 degrees. So most of the change already you can see is related with a purely regular thermal effect. However, if I look now further away from the Fermi energy, I see these shoulders. These are the famous H-bar omega wide non-thermal electron shoulders, which are were so important claimed to be important in the context of photocatalysis. So the good news is that if I compare these values to what I would have in the purely thermal case, which is just straight lines, then I see that already the illumination provided me many, many more orders of magnitude number of hot electrons. It can be 10, 15, 20 orders of magnitude, easily more high energy electrons compared to the thermal case. These are fantastic news. That's exactly why people originally claimed that these can be useful. However, if I compare the values I have these on the shoulder, here on the shoulders compared to what happens close to the Fermi energy, you can see a big difference. You can see 4, 5, 6 orders of magnitude easily between these values. So still the amount, although this is more than thermal, it's the amount of energy that is contained in these systems. Sorry. The amount of energy contained in this system is already seen to be very small. We'll soon see this more clearly. So, all right. So this I'll skip actually. What I want to do now is to look at the cross-section, to take a cross-section at a fixed energy for different illumination levels. And when I plot it here, I can see that, in fact, the number of hot carrier, hot electrons, is linearly proportional to the illumination intensity, okay, or to the square of the local electric field. Okay, I plot this result again, and indeed the slope is 1, and this allows me to extrapolate to higher energies, and basically to ask what should be the intensity, the incoming intensity, at which the hot carrier population will be order 1, will be a significant part compared to the thermal distribution. And the answer is the extremely high intensity of 10 to the 11 watts per centimeter squared. This is obviously non-realistic for a continuous wave illumination, but on the physics side, it tells us that reaching inversion, if you wish, in metals is not so realistic. It in fact tells us that this value is in a sense the saturation intensity, the intensity at which the rate of excitation and the rate of relaxation is comparable, okay? So once we appreciate this, we can make a simple comparison to, say, a dye molecule. In a dye molecule, we know that saturation intensity is about 10 to the 5 watts per centimeter squared. And the relaxation time, which determines the relaxation rate, is about a nanosecond. So this clearly shows us that the results we got make sense. Indeed, since the saturation intensity in metals is about 1,000,000 times more than in dye molecules, simply because the relaxation rate in metals is 1,000,000 times faster. So in a sense, this is it provides us a very simple physical intuition of what's going on in the system. It also allows us to come up with a very simplistic two-level system type expression for how many non-thermal carriers you could expect. And you can find this simple formula in this paper, so you don't need to go through our complicated formulation in order to get the actual distribution. So this is very convenient. This also tells us that the number of hot electrons depends only on the local field, and it's independent of the particle size, particle shape, on the host properties, or external temperature, quantization of electron state. All sorts of claims about this dependence have been made in the literature, and they turn out not to be correct. Okay, so far I showed you the distribution. Now it's time to move on to looking at the macroscopic properties. The first of those is to look at the temperatures. So I'm plotting here the temperature as a function again of the incoming intensity of the local field. As you can see, it grows linearly. So we can see two things. First of all, the electron and phonon temperatures are nearly the same. So this already justifies the use of single temperature models that has been so common in the context of thermoplasmonics. That's probably the first ever proper justification of this, although this is not a big surprise. This is just reassuring. Another reassuring fact is this linear dependence on the square of the electric field, which is in agreement with this classical model. Notably, this is not a trivial result, because the dependence on the of the temperatures on the electric field in our model is complicated, pure, strongly nonlinear, yet it reproduces this simple intuitive results. So this is quite reassuring. Now, I reach potentially the most important finding of the theoretical study, and it's essentially the fact that we are now able to answer the basic question we started with. How does the energy of the system split between heating the electrons and heating the phonons and generating non-equilibrium? What we see is very, very clear. We can see that the amount of energy going to electron heating and phonon heating is more or less the same, and it's way, way, way higher than the amount of energy going to pushing the system away from equilibrium, much higher than the amount of energy going to generating non-thermal electrons. Okay, so importantly, as you go to lower intensities, essentially the generation of non-thermal electrons is essentially completely negligible, and we only have heating. Even if the heating is small, it's only heating that you get at low intensities. And this tells us that unlike what you may have been able to see from the literature, it's not possible to generate non-thermal carriers without significant heating. And in fact, the efficiency of hot carrier generation is truly abysmal. And the important point to emphasize is that this comparison is done for the first time, because our formulation is the first one that is able to treat thermal and non-thermal effects on the same footing. Okay. So now that we have this result, we can go back to the question we started with and try to answer what is the reason for the faster photocatalysis. We can make a very simple prediction. So our results show that the non-thermal distribution grows immensely, but let's say 10 orders of magnitude more than in equilibrium. Then the simple Arrhenius law, or simple Fermi-Gordon rule, or even intuition tells us that if that's the case, and since the reaction depends on how many high energy electrons we have, we should expect the reaction to be about 10 orders of magnitude faster.
Jonathan, I'm sorry for interrupting you.
Yeah.
I just had some troubles with this sound. Could you turn on the previous slide?
Yes.
Yeah, so maybe I was missing something, but so maybe I missed something during your talk. But like, at what time moment do you plot this distribution? So because like,
ask again.
What time scale?
At what?
This plot. At what time scale?
Okay, this is the steady state distribution. I mean, everything I've shown is for continuous wave illumination, so I'm looking for a steady state. Okay, so basically, if I go back, well, we are balancing all these three terms and looking for a steady state distribution. This is what I argued is what is relevant for all these applications in chemistry. Okay? And on the physics side, this is the exactly regime that was not studied before. Okay?
So basically in CW regime, you can just neglect any non-thermal electrons, yeah? So like those are values.
So it seems. So at least the efficiency of generating the high energy electrons is a very, 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 very low. Okay? Yeah, so that's exactly the point. This is exactly the opposite from what people have been claiming and the underlying motivation to do all these faster chemical reactions. Okay, so I'm getting to this. So basically, yeah. So
Yonatan, we have another question from Alexander Petrov.
Yes.
It's a connected question. Basically, we are considering here a steady state, and you say that, okay, of course, you can speed up reactions with temperature, and then steady state is important. But some reactions require to pass certain barrier. Like let's consider a chemical reaction as photo effect when electrons are emitted into electrolyte, into some surface species.
That's the typical scenario, yes.
Thermalized electrons, they do not contribute at all. And the only concentration of hot electrons is relevant for the reaction. So it's not clear how, I would say your discussion should be separated. Basically, you discuss now only reactions which are going also without the photons there.
So I think your question is good, but it would probably best to keep it until I present the analysis of the experiments, and then I think we will have be able to have a more efficient discussion.
Okay.
Okay. So if I don't give you an answer, then do ask me again. So I'm really now at the crossroads. Okay. So we have this very, very specific theory, which says that predicts that the reaction should be much, much, much faster. Let's say 10 orders of magnitude faster. However, as I pointed out in the beginning, the experiments only reported 110 times faster reaction. And this implies an unavoidable conclusion, specifically that hot electrons are extremely unlikely to be responsible for faster chemistry, and thermal effects are much more likely. Okay? That's at least the prediction of the theory. This, as you can imagine, put us at complete odds with all the published experimental results by all these famous groups. So we really had now to try to reconcile our claims with these published experimental data. And this forced us essentially to start playing detectives. Okay, to really look into the experimental data and to see if we can get any trace, any relation to our theory. Now, what I've said so far has been pure theory. I appreciate that this might have been difficult for many people to follow. From now, if you lost me, that's a good place to pick up again, and we'll basically are doing a 90-degree turn and do a different start over in a sense by looking at some of the famous papers on the topic of Plasmon assisted photocatalysis. This is going to be very, very easy to follow. So do, I hope you are able now, you will be able now to follow me more easily. So to be more specific, we'll start looking specifically at one of the seminal papers in the field performed by the group of Naomi Halas. It has this peculiar title. And basically what they did in this study is to put gold nanoparticles on titanium oxide and to measure how quickly H2 molecules break down, dissociate. Okay, so this typically this reaction is very hard. The molecule is very stable because it requires 4.5 electron volts to happen. The claim of Norlander and Halas and Emily Carter has been that the presence of the gold nanoparticle opens up a new pathway which involves 1.8 electron volt, and this should exponentially increase the rate. So let's look specifically at what they have shown in the experiment. So they have measured the reaction rate as a function of time. Initially, they were in room temperature. And once they turned on the light, they have seen an 8-fold increase of the reaction rate. Okay. They also measured the temperature. And they saw that the temperature has gone up by 6 degrees. So then they said, okay, let's do a control experiment. Let's heat up without light. You can see the setup here. Okay, they have the temperature coupled, the temperature measurement, the thermometer, the heater, and the system. Okay, and they now illumination came from the top. Now they said, okay, let's not illuminate, but let's heat up from below to this by the same amount, by these 6 degrees. And they saw that there's hardly any change. This allowed them to conclude that the faster reaction happens here because of these non-thermal carriers. And essentially all this new field has gone crazy with excitement. Okay. However, if you look at their own setup, you might become a bit suspicious, because you can appreciate that while the catalyst sits here on the top, that's the brown layer, the temperature measurement has been done 3 to 5 millimeters away. This is Halas's plot. So you might suspect that maybe you might question whether the temperature here and here is not the same. And in fact, we are pretty sure that we can prove that this is the case. So this suspicions led us to look more carefully at the experimental data. So specifically, we look at this more systematic plot of the results, where again, the rate is plotted now as a function of the temperature here of the thermocouple. And this is done for different illumination levels, with 0 illumination and various other levels of illumination. So let's look at this more specifically. What we did is initially took these blue points, well, these are black here, right? And we performed the so-called Arrhenius fit to this set of data. Okay, Arrhenius, as you can remember, is probably the most basic chemical theory. It's very easy to perform this analysis. It's essentially what the first thing that chemists learn in university to do. And when we did this fit, we find that the activation energy is 0.23 electron volt, which is very different from the claim in the original paper. Now, the original paper did not do this Arrhenius fit at all. Okay, this 1.8 EV came from some sophisticated density functional theory calculation. Okay, this is obviously much simpler. And once we have this, we know the activation energy. The next thing would be to understand what is the temperature, say, for this set of points. So we asked ourselves, what should be the temperature in the denominator to explain this 6-fold enhancement between this point and this point at room temperature? And the answer is 66 degrees. Not 6, like they measured, but actually 66. Now that we know this, we can essentially predict what would be the reaction rate based on the temperature of the system, or how much extra temperature is generated by illumination, and as a function of different illumination levels and different heater temperature. And what we see is that there's a perfect match between our purely thermal prediction, and which is based now on the actual temperature of the system, between that and the experimental finding. In fact, now that we know everything, we can reproduce also the data of the middle lines. So this is how it looks. You can see with essentially no fitting parameters, we fit the data for these 2 lines, also all the dots, all the green dots except for one, we fit perfectly with a purely thermal theory. In fact, we can shift these curves and plot, instead of the measured temperature, we can plot the actual temperature. And you can see that essentially all these curves correspond to different, to the same experiment done with different proportion of external and light-induced illumination. Okay, so this means that all the data in this seminal paper by Naomi Halas, which is famous for hot electrons, in fact can be explained without anything that has to do with electrons, with the pure 19th century chemical theory. So we have two explanations. On one hand, we have a speculative, empiric claim by the Halas group. On the other hand, we have a fully quantitative, simple theory, a thermal theory that is based on 19th century science. And this already a person like William of Ockham, Franciscan monk that lived in the UK in the 13th century, already appreciated that the simpler explanation is far more likely to be the correct one. In fact, this so-called Occam razor is what we do almost always in science when we are trying to explain experiments. All right. So once we did this, we asked ourselves whether this was a one-time glitch. Maybe this just one paper that went wrong, and the others are fine. But then a quick search and looking at maybe the second most famous experiment on the topic by the group of Suljo Linic from Ann Arbor, we were able to perform the same procedure, and again to take the experimental data. This is a plot from the paper where the symbols are the experimental data. You can ignore here the dashed lines, which are just guides to the eye. And to do the same procedure, copy the data, do the thermal theory, and we have a perfect fit for the experiments, with essentially the bare minimum of fit parameters and no unbased assumptions. Okay?
Yonatan, excuse me?
Yes.
This is Anton Samusev. So I'm wondering, you're relying on the fact that those all groups and experimentalists so are not precise enough in measuring the temperature, as far as I understand.
Correct. Yes.
So okay, that might be maybe in a work, on a couple of works, but so what should be the reason? I believe that good experimentalists should check that they have the stable temperature, so they should avoid this this temperature, so this heat flux away from the system, and so on and so forth. So that's my comment. Basically, I propose that we just so emphasize that we do this. So you do this under assumption that the temperature is measured wrong, and I'm not sure that you. So we can claim that it is done indeed.
So if I want to rephrase what you're saying, you're surprised. These are famous groups. How could they get the temperature wrong? So I must share the surprise with you. Yes, we were also surprised, but the evidence is quite compelling. I hope you will agree. This here is their schematic plot. They never denied ever that they measure the temperature away from where the particles are. And you don't need to be a scientist in order to understand that it might be, the temperature here might be lower. You need to be a scientist in order to understand how much this difference is. And this is essentially what you did. Now, indeed, so far in this experiment, we have looked, we only deduced the temperature from the experimental data. But what we did for the Linic paper, for this system, I think it's, for this system, what we also did is we're able to extract all the data about the particle density, particle shape, etc., and to calculate the temperature. And what we got is essentially the same number, or very close number. I'll show this later for another paper, the same value of heating that we could have expected from a calculation, the same value we got from the fit. So this made us very confident that what we are claiming is probably the correct explanation. Okay, so we have two orthogonal ways to deduce the temperature. One through the data, one through an independent calculation. Now, of course, this is not a perfect proof, but this shows a much more likely explanation. If you combine it with the fact that the original studies did not measure the temperature in the right place, which is not a speculation, this is a fact. They put the thermometer not in the right place, then I think we have a compelling case. And indeed, at this point, we wrote down a paper. We were extremely excited. And we, before sending it to publication, we sent a paper to a colleague in the Hebrew University. And he said, wow, guys, this is really, really nice. But have you seen this? This paper. This came out a week earlier in Science. We looked at the title, which says quantifying hot carriers and thermal contributions in plasmonic photocatalysis, and we got a heart attack. So it seemed that the Halas group, 6 years after the original paper that we looked at, realized that they had a problem and they fixed it. Specifically, what they've done is to use now, not only to measure temperature, not only with a thermocouple, but also with a thermal camera, to actually get the temperature of the particles. And then they compared the reactions with external laser heating, and again they concluded that heating is negligible, and what you have in this specific reaction, it's a different reaction by the way, is again dominated by non-thermal high energy electrons, the so-called hot electrons. So we were devastated for about half an hour, at which point we were able to run the same procedure again on the data published in this Science paper, and again produce perfect agreement with all the data. Again, what we did is we extracted the activation energy from this set of data measured at zero intensity, and then fit all the other data, as you can see here. Again, here the lines here are not theory. There's no theory in the Halas paper. These are just guides to the eye, whereas our lines here are just the theory that we obtained. So this made us, gave us confidence again. We were able to produce additional, essentially all the other data in the paper we were able to do very, very quickly. Actually, the credit here should go to Yoni Dubi, which I mentioned, who did all this beautiful work. And again, my postdoc, Dr. Ben-Gurion, was able to extract all the data on particle density and the thermal properties of the host, an illumination scheme, etc., and to come up with a calculation that provided a value for how much the system heats up, which is essentially similar to what was extracted from the fit to the experimental data. Okay. Now, as you can appreciate, again, now the question remained: what is? Or I should go back. All these results were published then as a technical comment on the Halas Science paper that came out about a year ago. In that exchange, in that technical, obviously, the Halas group had a chance to respond. And this ensued in a very long discussion on many technical problems, not only the data that I showed you before. We also were able to understand where the experiment went wrong. As you can appreciate from the list here, they went wrong in many, many, many places. And this ended up with in a very unusual publication that I encourage everybody to look at in OSA Continuum. All these very long list of errors in the experiments were identified almost primarily by a very talented colleague of ours, Josh Barban, again from the chemistry department in our institute, and he pointed out so many problems about how they operate the camera and how to choose various properties. There's fundamental flaws in their understanding of the nonlinear response, and at the end, also incorrect normalization, which is a true problem of this experiment. So do ask me later if you want to see a bit more details about where things went wrong. It's actually quite funny. So, and I hope in that sense, Anton, this will convince you that even the good, excellent, famous groups sometimes make unbelievable mistakes. Anyhow, so at this point, so the papers have been published, and you can ask yourself now whether this is the final word, whether hot electrons are pure fake news, or maybe there's still something to them. So at this point, we have to admit our simple theory, thermal theory, does not explain every single experiment that has been published already. Obviously, we haven't looked at all the billions of papers that have been written, but there's some specific ones where, for instance, reaction selectivity has been demonstrated under illumination, which we cannot explain. There's other approaches which isolate thermal and non-thermal contributions to the reaction with various ways. And obviously, I think this relates also to the question that I was asked about what happens when the electrons have to really tunnel through a barrier, Schottky barrier type interface in order to either generate a reaction or more typically to be used in a semiconductor for detection. So there's a big branch, successful branch of experiments and even applications, also led by Halas, but also by Uriel Levy and Jason Valentine, also Moscovich, good, very, very good experimentalists that have been unequivocally proved the role of hot electrons. So in that sense, our point is that while so far there's been a lot of experiments and very poor theory, now our theoretical tools, both for the non-thermal distribution and for the proper thermal calculations, can be used to quantify thermal and non-thermal effects correctly in essentially all the experiments that have been done and those experiments that will be done. And just to give you an example, this already has been done by the group of Vlad Shalaev and Sasha Boltaseva together with Yasher Khurgin, published recently. What they have done is a very careful thermal calculations and measurements in a system with titanium nitride, never mind the details. And what they have shown that hot electrons action has been indeed confirmed to be responsible for a chemical reaction. However, this happened in an extremely dilute suspension and for a reaction which has an extremely low activation energy. So these conditions are somewhat ironically exactly the opposite to the conditions under which the whole idea of hot electrons came up with. So at this point, I think we are now quite confident with our results, and we hope that our approach will become standard in future experiments done on this topic. So to summarize what I've shown you so far, very quickly, I've shown you a self-consistent model of thermal and non-thermal effects. I've resolved the paradox, so-called paradox, how to that it is possible to define a temperature for a system, although it's under illumination. And we've shown that the original claims that about the ability to generate many non-thermal carriers without heating is probably wrong. And that the claim that most catalytic improvement is due to high energy electrons, at least in the experiments that we looked at, which are again the most famous one, most visible ones, is extremely unlikely. In that sense, the efficiency of non-thermal carriers generation is very poor, and now we can really embark on a re-evaluation of previous experiments, work with a very quantitative, reliable theory. Just in the last maybe few minutes, I want to say very brief words about where do we go next. So I suppose you can appreciate that the theory that we have presented has been fairly simple, phenomenological even, and we really need to extend it in order to get a better agreement with experiments. This would include accounting for nanoparticle geometry. Some of this work has been done. Accounting for non-uniformity in transport. We already have a couple of papers on the topic. Account for tunneling and this crossing of Schottky barriers. These are elements of the theory that have been performed, but they have to be combined properly with what we have done. And this is something we intend to do. We also want to extend the work to interband transitions, first in semiconductors, to try to understand how the non-equilibrium looks in semiconductors. Apparently, this has not been done. This is just a glimpse into how does the non-equilibrium look in the conduction band and valence band. You can see very different from what we have in metals. Then combine this with the Drude metals that we have studied so far and have a more realistic picture of what happens, for instance, in gold, where interband transitions are important. We also want to go beyond photocatalysis. We now have a framework that allows us to compare coherent non-thermal or coherent nonlinearities that come from non-thermal electrons and nonlinearities that are generated from incoherent heating effects. And in that sense, we will able to again merge the theory and have a consistent theory that describes both sort of effects simultaneously. This is nothing that not something that has been done so far. These topics have been these effects have been studied separately. And this way you hope to explain, be able to explain decades of studies of nonlinear properties of metal dielectric composites. As I promised, we are also looking at metal luminescence. This is a particularly interesting problem because it seemed, although that there's been decades of studies of luminescence for metal, there's been no proper theory, at least not electronic theory, and many arguments about the origin of the effect and contradiction measurements, etc. And this has become even more important in this specific context because recently anti-Stokes emission has been used for thermometry by various important groups. Each suggested its own protocol for this thermometry, and there's a huge discrepancies. Just to give you an idea, for instance, the group of Stefan Link from Rice has performed measurements of temperature, extracted temperatures from gold nanorods, and the results have been extremely noisy. They concluded the temperature could be under some conditions 1500 Kelvin plus minus 1000. So you can see that these protocols are quite problematic. There's also various incorrect extensions of the theory. So what we offer is, first of all, a complete electronic theory, and the results I'm now briefly going through are purely unpublished. So this is just a glimpse again. We use the knowledge of the non-thermal distribution in order to compute the emission rate. We also complement this with complete photonic theory, which also has been partly missing, which is based on the model approach that I mentioned. We can calculate the Purcell rate as a function of position inside the particle and this different spectra, which is associated. And finally, we provide insights on the spectral dependence and electric field dependence, and provide improved thermometer protocols. This all is in the pipeline. Hopefully, we'll be able to publish this theory, and we are very much looking forward to collaborating with experimentalists in order to verify these predictions. So at this point, I would like to finish by quoting from a famous scientist. So Richard Feynman taught us that there's plenty of room at the bottom. He meant in the nanoscale, but I actually mean the bottom of the map of Israel. In Beersheva, we are always looking for good people to join the team. I hope that I have convinced you that there's good science that we are doing and interesting problems. If this is not enough, then maybe a typical weather forecast from the winter, actually. I appreciate now is maybe less impactful, but if you think about the winter weather compared to what happens in St. Petersburg, hopefully this might be appealing to come and see us in Israel, in Beersheva. And if not that, then maybe the beautiful desert that we have, everybody's welcome. And at this point, I will stop, and I'll be more than happy to answer as many questions that you may have. Thank you.
Thanks, Yonatan. Colleagues, we have a bit time for questions, not that much, since we are already 1 hour 25 minutes. Do we have any questions? Yonatan, I would like to start. So from your model, it is clearly seen that you can explain the data by some excessive temperature that you add to the formulas, and basically you say that okay, this temperature may originate from the experiment, which might be performed incorrectly by a few groups. Yes. So I'm wondering, could be there any other reason, for example, theoretical, fundamental reason that would provide this kind of excessive temperature? Anyway, from this you get an additional factor, so exponential of some formula depending on this excessive temperature divided by the measured one. So could be any other reasons?
I'm not sure that I understand your question, but in fact, we mentioned the incorrect temperature measurements in the early papers. There was an attempt to fix these problems in the latest science paper. This wasn't done correctly at all, and I can show this in more detail later. But essentially, the real, I mean, so some may, the Halas group may argue that, you know, they did some measurements and they did the controls properly, but actually what the real problem they had, which is still happening in the newest papers, is that they have, the control experiment is done on a different sample, which has a different volume. And what they do is they normalize the data, the reaction rate by the volume. This is completely wrong, especially since the systems are different, since the temperature distribution is different. This really is at the heart of the failure of their arguments. And to be specific, for this science paper, they were claiming that the hot electron effect was happening only on the surface, and when they normalized by a factor, to correct for this, they normalized by a factor of 30, and showed that the so-called non-thermal effect was 30 times higher than the thermal effect. But this was a pure result of their unnecessary normalization. So really, my answer is that there's layers over layers of problems in the common practices. I mean, we focused on one or two groups. Maybe this is not fair, but problems have been found in many others. We should be fair also to say that measuring temperature is difficult. Measuring correctly, measuring it on the nanoscale, measuring it with a high resolution is difficult. But there is several groups. I can mention the groups of Emiliano Cortes, for instance, and I mentioned the group of Shalaev and Boltaseva that have measured the temperature properly. This can be done, and it should be done this way.
Okay, colleagues, any other questions? So if not, Yonatan, may I ask you a very short question regarding so returning to the title. So hot electrons, reality or fake news? Okay,
great. So I think as far, what the message of my talk is that as far as these photocatalysis, famous photocatalysis experiments, the claims there for hot electrodes have been, unfortunately, fake news. And I'm saying unfortunately really because, you know, if the claims about the ability to make reactions so much faster have been real, this has been a great promise for our energy industry, for instance. So in that sense, in those papers, it is indeed has been fake news. However, in other problems that I mentioned, it's probably those papers, and specifically in the studies of photoluminescence, hot electrons are absolutely, surely responsible for the effects we have been seeing. So in that sense, they have been reality. So the answer to this question is obviously complicated. It depends on what context. And I think this is always true. In particular, this is also the case for the problems that we have been looking at.
So, okay. Yonatan, thank you very much for a very large and interesting talk. So I would like to briefly announce that the video of the seminar will be available at our YouTube channel. So you may also subscribe to our events and visit our web page, which is is enhanced and looks better now and more convenient. So I would like to briefly announce the next optical seminar. It will be given by Sergei Ginenko from University of Calgary, Canada, and he'll be talking about indoor organic photovoltaic devices next Friday, and the seminar will be at 5 p.m. St. Petersburg time. So Yonatan, thanks again.
Okay, thank you very much. It was a pleasure.
Yonatan, are you still here?
Yes, I am.
Just to clarify, I wanted to ask, so you have found that you can explain all the results by adding some excessive temperature that was probably measured incorrect.
No, we are saying
so
that the temperature that was, let's see, which is the...
Yeah, in the denominator there. Here, for example.
When the x-axis is based on the measured temperature, this is actually Tm here.
Yeah.
Okay. It's not, when it's not the right temperature, then you may have the wrong conclusion. But this was because the temperature was measured in the wrong place.
Yeah. So regarding this picture, being an experimentalist, what I can comment to you. So if you have a good thermostat, then you don't have any losses of heat from the chamber, not much losses. So depending on the quality of your chamber, you may assume that everything is balanced and you have the equilibrium, and the temperature difference may be very, very small. So this all depends not only on the distance, but also on the how fast you lose your heat. For this reason, this thermocouple may provide relatively good measurements. So it does not necessarily mean that...
I don't think so, because I mean, distances here are large. What really needs to be done, and it has been done by several groups, is to put a thermometer inside the catalyst. This is not difficult. It's possible, okay? And then you see several things. First of all, the temperature is much higher than farther away. And indeed, this difference we can calculate. It's easy. That's a simple thermal calculation that the first year student can do. Now, this is shown here as like one line, but it's actually 300 micron thick. What you see is that also within the layer of catalyst, there's severe gradients. I haven't shown this here because I really only touched the surface, but the proper thermal calculations and also proper thermal measurements that have been done since show that there can be, in this experiment, for instance, there's been a drop of hundreds of Kelvin from top to bottom, and 100 Kelvin from center to side. Okay, so the whole system is extremely non-uniform, and this is because the heat is generated at the center, right, and it leaks out, and these regions get heat just from one side, not from two sides. Okay, so there's severe gradients over there which really have to be resolved properly in order to perform the correct control experiment. Okay, so you can appreciate that if you want to have control experiment, it has to have this exact same temperature profile with light and without light. And this is essentially impossible to do. Okay, so, unless you go maybe to single particle.
Okay, but again, what I was saying that probably all those heaters have the feedback system that control and stabilize the temperature.
Yes, but you cannot avoid if the systems are that big, 300 microns, that's a typical value.
Yes, but all your
gradients inside.
All your temperature gradients will depend on how fast your heat leaks away from the chamber.
Of course,
if it is a perfect non-leaky chamber, it will be all right. In a year, I don't know, in a day, in a week, everything will be stabilized. Do you agree with that?
Stabilized, but non-uniform in space.
But why? If we don't lose the heat, the energy, we do not heat up the heater anymore since the temperature is stabilized due to feedback, and everything should be stable.
Let's think about again this system where it's illuminated from the top. Okay.
Yeah, I see.
So we calculated. Also, this was corroborated by the claims in the Halas book that the penetration depth of the electric field in this system has been about 10 microns. Okay? That has to do with the density of particles, etc., etc. So it means that only the top, there's absorption of light and generation of heat only on the top layer of the system. Okay? So it means that the top is much hotter than the bottom. And for this specific
but this
system,
again depends on thermal conductivity of the sample, you know.
Of course, yes. But these samples, again, I didn't get into the details. These samples are essentially highly porous oxides with particles inside. So the thermal conductivity is dominated by air. Air in the pore. This is like 90% porous, if I remember.
Okay.
So you have severe gradients inside. So once they were, and this makes the whole system much more complicated. Now, one of the successes of the Shalaev group that I mentioned is that they use the liquid and very dilute solution of particles, which made the temperature very, very uniform. In that sense, this allowed them to have a proper control experiment and really to pinpoint the contribution of the hot electrons. Okay, but this was done much more carefully. Okay.
So, by the way, what for example, George, who organized the seminar, is doing in the experiments, they are looking, so they are measuring the temperature by means of Raman. So they obtain temperature with a very good precision and a broad temperature diapason.
Raman or molecules that are used as probes?
So yeah, your Raman line shifts with the temperature, and from this you can estimate it with a good precision. So you just got an optical measurement.
Yeah.
And it's quite a good way to do so.
Okay.
Okay, Yonatan, thank you very much. So I have to go to the next meeting.
Yeah.
So we will prepare the video and we'll send you.
Perfect.
Before we put it. So thanks a lot again.
Yeah. Thank you. Bye-bye.
Goodbye.